Okay, everyone, this is our very first introduction to radiology physics, and hopefully you can get a little bit of information from what I present today. I want you to understand that this is all from your textbook that you have from Elsevier, but I've changed the format of the presentation just a little bit to go along with my teaching habits. So hopefully I won't bore you to death, and you're not required to listen to this if you don't want to, but I think it would really help you in the long run. So let's get started. The objectives that you see here today are actually taken from the text. These are a little different from the objectives of the module that you will see. And the reason of that is because in the module, we've just kind of hit the basics, and those objectives include Chapter 5. These are the objectives of Chapter 1, and all of these are very important, not only for this particular course, but for the profession itself, so that you understand every bit about it that you need to know. We're going to talk about the discovery and evolution of X-ray. We're going to talk about fundamentals of physics. We're going to define and use radiologic units of measure. Then we're going to talk about some permanently installed radiographic equipment, and then the general components of those, okay? So here we go. Here's the first person that you need to know about, and the original or the actual pronunciation in German is Dr. Wilhelm Conrad Röntgen, and that's the O with the two little dots. Please understand that if you see this anywhere that it's Roentgen, it is the same person, it's just the way it's written, but I will still kind of say Röntgen because that's what we always hear when we talk about the discoverer of X-rays. He was born in 1845 in Germany. He got his PhD from the University of Zurich in 1869, and he was the director of Physics Institute at the University of Würzburg. So those are very important things. Now, what you also need to know is that here, we'll just go to the next one. The exact discovery details vary about what Röntgen did, but the date that we have listed as the discovery of X-rays is November the 8th, 1895. You will actually probably need to be able to relate that date back one day. And this is when he was preparing experiments involving a cathode ray tube. So late on a Friday afternoon of November the 8th, he was working in his lab, he had some experiments going on, and then after he had set up the tube and was preparing for those experiments, he actually covered the tube with black cardboard, and then he noticed that there was some fluorescent materials nearby, and that was specifically barium platinocyanide painted cardboard. Now, fluoresce we'll learn later when we talk about fluoroscopy, but it just meant that it glowed. And because he didn't understand why it fluoresced, he went to investigate. Now, again, this was on a Friday, and so he took the weekend and then the rest of the next 7 weeks to investigate and figure out what exactly was causing that. And he determined there was something called X-ray. He speculated there was a new kind of ray that was responsible. He took the weekend, he repeated his experiments, made his notes, and then he actually called it X-ray temporarily because X is a designation for something that's not known, but that name stuck. They also, after he published some papers about it, they call them Röntgen rays, and the images were called Röntgenograms, or you can say Röntgen rays, Röntgenograms, it's all the same thing. But just so you know, and if you read my introduction, you know, I always say I went to X-ray school, but that's what X-rays are. That's when it was discovered, and it was very, very important from that. Now, we don't know a whole lot about his experiments from those 7 weeks to when it was first produced, because once he died, upon his death, he had asked that all of his notes from his experiments were actually destroyed. So what we have is what we just have on the books. So again, remember that date of November 8th, 1895. Now, he investigated this so thoroughly that he discovered and talked about just about every property of X-rays that we still know today. Now, we have improved the way that we actually take images using X-rays, but it is still the same properties that he learned back in 1895. As part of his investigation, he actually asked his wife to allow him to photograph her hand. And you have to understand, back in the day, they actually thought this was a way to photograph. They didn't realize that it was damaging at that time. So on December the 22nd of 1895, after discovering it on November the 8th, he placed his wife's hand in the path of the rays, and he observed it after he developed the plate. And you have to understand also that that one Röntgengram that she took actually took about 20 to 30 minutes to make that image. And when she saw this, she actually said, "I have seen my death." So he took, and I want you to look at this picture right here very well, and I'm going to do this around that ring and see how it's pretty dark here, but that one's known as the very first x-ray that was taken of his wife's hand. And he completed his investigation, and then he wrote 3 more papers about this subject, and he published that on December the 29th in Würzburg, and then he took it to the society to give a presentation in January of 1896. And from there he just became even more well known, and he did a lot more research into these wonderful x-rays that we now know. Now, here's another x-ray, and what I want you to notice is that this one was taken later of this gentleman, Albert von Klicker, and this was one of his friends, and he took this image at a public lecture. So not only did he do it of a friend who didn't necessarily need an x-ray, but he did it with other people standing around. And with that, he noticed the picture is still similar to what his wife's was, but between the time from he did his wife's hands to this one, he made the image just a little bit better. You can see these bones better, and then you can see a ring here too. So if you ever see one or either of these particular x-rays, know that one was his wife and one was not. When he actually gave this report in January, a newspaper in Austria gave him the honorary Doctor of Medicine degree. So he already had his doctorate in physics, but they gave him a doctorate of medicine, and he is now considered the father of diagnostic radiology. And that's because from this, they took this and was able to actually use it for medical purposes. So all of that's very important, because at first it was still just considered a photograph, and it was only talked about for a long time. Of course, it was only a couple months, but then they realized the radiology implication of that. So here's some fun facts about Wilhelm that you may not have known. As a boy, he was accused of drawing a picture of his teacher, and it wasn't a nice picture, so they expelled him from the boarding school he was at. But he did not actually draw the picture, someone else did it. And he didn't have the guts to tell them, well, I didn't do that. So they kind of thought he was a little bit of I guess in those days, that would be the epitome of a hoodlum or something, who knows. So they thought he was just a bad kid. But he ended up going to public school from the boarding school, and he didn't have the qualifications to go into the physics program he wanted, so he went into mechanical engineering. And then he eventually got into the graduate school for physics after showing that he did know what he could do. And his first work was actually published in 1870, way before he was playing with his tubes and cardboard, and they were about electricity and gases caused from heat. And then, like I said earlier, it's hard to establish a full and detailed account of his story, because upon his death he did ask that all of his notes be destroyed, and so they did it. I mean, they thought enough about him to value his wishes, and that's what he did. He died in 1923. He was 77, which during those times, 77 was a long time to live. He died of colon cancer. Now, his wife died before him in 1919. And there's always been speculation that maybe she died sooner than he did, because he used her in a few more experiments than just that one hand that we all know about. The tube that Wilhelm was using was called the Crookes tube, and you need to know about that because this Crookes tube was actually already around before he was working with these things. It's a glass cylinder, has two metal electrodes, and when you put high voltage on them, then the electrons travel in a straight line from the cathode to the anode, and that's what produces X-rays. We'll talk about it later when we get into the actual tube and the way it makes, but this is the cathode and it goes to the anode, and then these are just a couple of different variations right here. Now, at this time, this is just glass and there's no shielding. So all the X-rays that were made were able to just be dispersed around. They travel around. So if you're standing there working with this tube, you're getting X-rayed at the same time. And this tube was actually invented by an English physicist named William Crookes. Now, he was born in 1832 and he died in 1919. And I want you to look at this date right here. He invented this tube in 1875. So he was already responsible for creating this tube and showing that electrons could be produced, but he never actually knew what those X-rays could do. So this tube had been around for 20 years before it was used by Wilhelm to make a photograph or a radiograph. And so Crookes is known for this. He was a British chemist, a physicist, he worked on spectroscopy, and he was the first to say that there were cathode rays. They traveled in a straight line. They actually caused fluorescence when they were on some substances, and that they can produce great heat. Now, what's even more interesting, after his tube was used to produce X-rays, Crookes invented a 100% ultraviolet blocking sunglass lens in 1913. So he's actually more known for making the tube and then producing sunglasses. And it's a shame, if he had been the one to see something fluoresce nearby, he may have been the father of X-rays, who knows. So anyway, little interesting fact there. So when I said these tubes were just sitting around and people played with them, I'm sure they were doing scientific experiments, but this was in the late 1800s, and this is visible in the center of it. So these guys are just standing here. He's looking at his hand through a scope, and then there's the tube right there, and it's just emitting X-rays everywhere. And then here's another one down here. He's putting his hand on a plate so he can take some radiographs. So you can see really quickly that they didn't know exactly what they were doing with these X-rays. So the early uses of it, they used photographic plates to expose these X-rays, and they created images. And then it was in around this time that they actually started using it for medical purposes. Physicians decided, hey, I can actually use it for something. And the public was fascinated by these because, again, they thought it was a photograph and it was a form of light. So in the early days, these tubes and generators were used and made images of people's body parts. Yes, some physicians used them for good purposes, but other people were doing it just for the fun. And then these exposure times were anywhere from 20 to 30 minutes. And if they were doing like this one right here, they're looking at this gentleman's abdomen, that could have taken 2 hours. That means that they were actually X-raying that person with X-ray for 2 hours to take one image. And so because of that, that's when we started finding out a little bit later that they were causing some burns, and then the people that were operating these instruments actually had electrocution because they didn't know how they were supposed to be grounded and other things that happened. So just some interesting pictures here of early X-ray use. Here's some other scientists that I think are very important for you to know. Thomas Edison, which is who we think about when we think about electricity, he also investigated materials' ability to fluoresce. So he has found that the calcium tungstate was the most effective, and he discovered the fluoroscope in 1896. So after Wilhelm found the X-ray itself, he made the fluoroscope, and that became the standard for medical X-ray. So he had a couple of things that he's known for. But he dropped off the X-ray research but when he did, it's because of this gentleman right here. Clarence Dally was Thomas Edison's assistant, and he was using him to practice on, and he actually died from the exposure. Clarence got so many burns on his arms and his hands that he got a cancer from them. They amputated both arms to try and save his life, but it didn't. He still passed away from it. Now, John Hall Edwards, right here, is the first person to use X-ray under clinical conditions. He radiographed a needle stuck in the hand of an associate, and then on February 14th of 1896, he used the first X-ray in surgery. So then there was another person right here, Ivan Romanovich, and this was in 1896, not long after Röntgen talked about X-ray. He radiated frogs and insects, and he actually put out there that not only did it photograph, but affected the living function of these frogs and insects. Now, it took them a while to realize the same effect to the frogs and insects were happening to people, and they didn't know that until these people came along. So, with the widespread experimentation with X-rays after their discovery, physicians, inventors, and everyone else started using it, and then came the stories of burns, hair loss, and even worse in the journals. So in 1896, Professor John Daniel and William Laughlin Dudley of Vanderbilt, Tennessee, and this is him right here, and this is, they were x-raying themselves basically, and Dudley was x-rayed and then he reported hair loss. So a child who had been shot in the head was brought to the lab, and before trying to find the bullet, then he actually used himself as a volunteer to see how long it would take, and by doing that they radiated him so much that his hair started falling out 21 days later. And so a plate holder with the two plates, towards the side of the skull was fastened, and the tube was put at about a ½ inch from the hair. So we'll find out later why there is a reason that we don't put these tubes right next to the body part that we're working with. Then there was Dr. Hawkes from an X-ray demonstration. Again, he would go around and talk about how great this tool was, and he received hand and chest burns. And then Elihu Thompson, he deliberately exposed his finger for demonstrations and got finger blisters. And then the first death of a woman was Elizabeth Fleischman, who was an American pioneer, and she died from all of the radiation that she worked on herself. So that, it wasn't a good thing, but at least from her experiments we have learned what we should not be doing with some of these x-rays. Here, and this is in your book, so I'm sure you've already looked through that book and you've seen these pictures. I love that they're black and white so that we don't have to be really grossed out. But because the radiation burns did not occur immediately after exposure, a lot of people didn't make the connection. So they thought that it was just an electrical effect that happened from these x-rays, not the radiation itself. And some people even thought that it was just part of sunlight, so it was a sunburn. And when this happened to their hands, all they knew to do was just to amputate it. So amputation and then gloved hands became identifying traits of the profession, meaning if somebody already had a hand that looked like this, they may put on gloves just so that they didn't scare their patients or their customers while they were doing it. Then the public decided by 1900 they improved their techniques, and so you see these products right here. They started recognizing that it was useful in medical care, but there was still a carefree attitude about it. And so the term X-ray became so popular, they were using it in poems and songs and plays, but it also became part of advertisements. Now, there was actually no X-ray in any of these products right here, but by using the word, they felt like it got them the advertising that they needed. So if they saw this X-ray golf ball, it's guaranteed to be that you won't have a cut. If you play golf, you understand what that means. But These are just some of the things that they used it for. Stove polish. So it cleaned your stove better if they put the word x-ray on it. And then x-ray tablets to cure your headache. Just a different way of using the term and getting that recognition out there. Here was an application that did actually occur though, and this was for getting your shoes fitted. And by getting your feet here, so let's see if we can do this. If you stood here and then you put your feet in this little hole and you kind of leaned against this board, the salesperson stood on this side, which is this, and would look at the feet with those shoes on and see if they fit correctly. Now, you have to understand, back in the day, we didn't have the 50 pairs of shoes that someone might have now. What you got was one pair of shoes that had to go at least 1 year and sometimes longer. So this way they could tell if it was fitting correctly and you had room to grow in. But if you think about the x-ray that was emitted, and especially if these were children, if they were just leaning against here, there's no protection. That wood did not actually keep that x-ray from radiating into the body. They also used x-ray for a way to remove hair, because they saw what happened to people who did use it on their heads, and so they said, oh well, let's just radiate them and then keep the hair from coming back. Well, by doing that they also possibly induce cancer, but that's another story. Okay, forget about all the history and all the fun that I just brought you. Let's talk about where we go from the beginning, and let's go to physics. So, what is physics? Why is it important to us as a radiologic technology? The dictionary says that physics is the study of matter, energy, and the interaction between them. It's the science of matter and energy, and it's the natural science that studies matter and motion. All of these things are definitions that can be applied to physics, but you have to understand that it is the branch of science that's concerned with properties of matter and energy. So right here, matter and energy is what's important to us in radiology, and we're going to talk about the ways that electricity, magnetism, radiation, all of these different things go together. Now, radiologic physics is what is important and vital to a radiographer or a medical imaging professional. We're going to learn what it is and how to use it so that we use it safely and responsibly, because we do use ionizing radiation when we use our equipment to take an x-ray. Then we're going to talk about how the x-ray produced goes to the imaging process, what it actually makes for us. And then we've got to know general physics. Then we have to understand the radiology concepts of it. And by doing that, we're going to go over some things called fundamental, then derived units, and special quantities that are important to us in X-ray. I found this really cool sign that was made a long time ago, but this is what I want you to know, is that radiation has to command our respect because it is not to be used lightly. And you need to understand from the bottom up why that's important every time we take an image. Okay? So, back to the basics of units of measure. Now, one of the unifying aspects of all sub-concepts and sub-disciplines of physics is the use of numbers. Numbers are a way to describe and quantify a specific phenomenon, and then you can communicate that to others. So you have to be able to know what these numbers are to even define what physics is. So with these numbers, there are different types of units. Now, the scientific community has been able to narrow down and standardize a set of basic measurement units. And then from that, you need to understand that there is something called the British unit. And even though it says British, that is what we use in our everyday language. And then there's something called Scientific International, or SI units. Those SI units are what is more common in the scientific world, and especially in radiology. So for everything that we cover, I'll be going over the usual numbers and then the SI units that go along with it. So now that we know that we have to have a number to describe something, we have to have a unit for that number, and then there's quantities. We need to know these three fundamental quantities right here, and they're very important to us to get started. So knowing that these fundamentals are then used to make derived units, then we can put them to our radiation units and make a little more sense out of it. So in case I didn't say that clearly, our fundamental quantities are mass, length, and time. Our derived quantities are things where we take the mass, the speed of light, the energy. Now this is just one type of formula. So E is energy equals mc squared. So I know all of you have seen these types of equations, but now I want you to understand we're going to learn how to get velocity, acceleration, force, momentum, work, and power. So all of those derived quantities are important also. And each of these quantities are defined using an agreed-on standard, which is discussed in just a little bit. But by putting these fundamental quantities together, the derived quantities are what then form the foundation for general physics, which is very important. Once we get the derived quantities, then we're going to talk about some special quantities of radiology, and those are dose, dose equivalent, exposure, and radioactivity. But you can't understand the dose until you understand the derived quantities, and then you can't understand derived quantities unless we go to fundamental. So from all of these, this is going to make sense of why radiation can damage. It's bad for the body, and if you're using X-ray or radiation, you need to be as far away from it as possible. So that's what actually this sign is saying to everyone. So in some places we use pictures or diagrams instead of words to make sure everyone understands. The skull and crossbones should be a symbol that everyone knows bad. Radiation is bad. Get away from it. So here we go. Here's our first units of measure. So we need to know mass, and we think about that as a pound. So all of us know how much we weigh, probably, in a pound, but do you know how much you weigh in a kilogram? Now, there is a way to actually convert a pound to a kilogram. I'm not going to discuss that. I just want you to understand that when we talk about kilograms, it's the same as a pound. Length, we think about a foot. Well, in the SI system, it's a meter. And then with time, the only thing that stays constant is a second or a second. So time itself does not change from the regular system to SI units. Yay, one thing that we don't have to worry about it. But once we go over each one of these, then we can use these fundamental quantities to then find some others. So what is mass? Mass is the quantity of matter. And when you think about matter, matter can come in three different ways. It can be a solid, it can be a liquid, or it can be a gas. So you need to understand that a solid piece of matter keeps its shape. It has a fixed volume. So we think about a solid matter just like this astronaut right here. He is in one shape. He really can't be changed. Now, liquid will move to where it forms the shape of the container, and it has a free surface, but it does still have a fixed volume. So if this box had water in it and then we turn this upside down, the water is still going to move to the bottom because of gravity and all that other stuff, but it still has the same amount of liquid as long as none of them come out. And then there's gas. Gas also forms to the shape of the container, and it's going to be the volume of the container. So it is only how much that container can hold. So this one's a little different from solid because this is fixed, and it's different from liquid because it's fixed. This one can only have as much as the container itself will hold. This is to give you an example of what mass is. So we have 120 kilograms. Now the weight is in newtons, but this weight is different because they're on the moon instead of the earth, but they both take up 120 kilograms of mass. So understand that mass is how much it takes up, not anything else. Not how much it weighs, how much matter it takes up. Now here's length. In case anyone didn't know, I'm here in Florida, teaching you here, and a length is the distance between 2 points. So how appropriate is it that I have some sharks? So here's a long shark, a little bit shorter, and then a little shark. Now personally, I think all these sharks are dangerous, but that gives you the distance between one to the front to the end of that shark, and each one's a little different, and then that distance is measured. We're used to miles, feet, inches. SI units are kilometers or kilometers, meters, centimeters, and millimeters. And then we can also have yards or meters and miles. So just knowing the different conversions is important, but know that we're going to be more concerned with the SI unit. You will need to know how to convert the metrics themselves, and when I say that, I'm talking about this. So our length is usually the base unit of a meter, and with that you can add these units to it. So there's your base, and then you can go up, so it'll be a deca, hecto, or kilo, or if you go down, so less than a meter is a deci, centi, and a milli. Here's a little mnemonic if you need to remember the order. King Henry doesn't usually drink chocolate milk. So usually is the unit itself, so that's just a meter. This can also be for a gram, so if you're talking about weight. So if we're talking about a gram, that's the unit. Well, you can have a decagram, a hectogram, or a kilogram, and each one of these is a step of 10. So this would be 10 times, 100 times, and 1,000 times. Now if you go below it, that has a little th on the end of it. So this is a tenth, a hundredth, and a thousandth. So same thing with the liter. Here's your liter. You can either go up and have more liters, or you can go less and then have less liters. So know those are the basic ones that you're going to use, and I can tell you most of the time it's going to be kilograms or kilometers or kilometers, however you want to say that, and a kiloliter. But you don't usually talk about it in the bigger parts. It's going to be the smaller ones. This is another chart, and you can just look at it later. Here are the multiples. It tells you how to, one would be right here in the middle, so that would be your unit. And then if you go deca, hecta, I want y'all to notice right here there's a K. Some charts have that as a C, so it can be either. So deca, hecto, kilo, mega, giga, tera, centi, milli, micro, nano, pico, femto, atto. You'll never go past nano. These three down here you won't need to know. But just so you know the symbols, know what it equals, the name, and then here's the symbol over here. So just like this M is always big, and then it says that's the most commonly used. So mega and a kilo are the most often used on the upside, and then centi, milli, and possibly micro down on below the unit size. Then when it goes to time, time is measured by a clock. There's no difference. You know the smallest unit is a second. Now, yes, can you have microseconds because that's less than 1 second? But there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 52 weeks in a year. You could take that then and make these estimates of how many seconds there are in a year by going throughout all of these. Not any different anywhere. All right. Okay, I took just a quick break to get me some water here. Now we're going to go into derived units of measure. So after knowing the fundamentals of mass, length, and time, and knowing their units of measure, and by the way, if you haven't already been to lab, you will kind of go over some of these things in lab, so that will help you also. But now we're going to talk about our derived units of velocity, acceleration, force, momentum, work, and power. Now, I can sit here and tell you about each one of these, but let's just move to each one individually. But to calculate these, you have to be able to figure out fundamental quantities and how to use them. So the first one we're going to talk about is velocity. Velocity is the motion of an object, and with that is equal to the distance traveled divided by the time necessary to cover that distance. So velocity, which is a big V right here, is distance, the distance it travels, divided by time, so d over t. Yes, in this equation up here, these are capitalized, but it's not in this equation. So please understand if you see small d and a little t, that those are correct. So it's a measure of how fast something is moving or the rate of change of its position. So we're talking about velocity in general. And so if we talk about the velocity of an object, let's pick a football. So if a football is thrown and it travels 60 meters in 4 seconds, what is its velocity? So it traveled 60 meters. Now we're not going to worry about what that is in feet or anything else. So you go velocity is 60 divided by 4 and you get 15. So the velocity is meters per second. And these are the units that go along with distance and time. Now, there's a possibility that you may at some point say if something has a velocity of 15 meters per second, what does that equate to in millimeters? Then you would use a different type of equation, and we'll talk about that maybe later on if y'all need some help with that, okay? Our second one is acceleration. So acceleration is the change in velocity over time. It's how quickly or how slowly the velocity is changing. So you just learned the velocity. And by doing that, then we subtract the initial velocity, and usually that's 0, and that would be 0, and then the final velocity. So that's F. So it's final velocity, subtract the original velocity, and then divide it by time. Now, because of that, this velocity is meters per second, this velocity is meters per second, and then when you divide that number, then it's going to be squared because it's saying how fast that it's going from original to final. So the rate that it changes is calculated by, let's take a car, and if a car is actually accelerates from rest, so it was going 0, and that's what you would put, its initial velocity or original velocity is 0, and then it goes into the final velocity is 36 kilometers per hour. Now, I said up at the beginning that it's usually meters per second squared, so we're talking about kilometers and hours in 20 seconds. Well, the first thing we have to do is change the kilometers to hours to meters per second. So if you have 36 kilometers, changing it to just a meter means it's 36,000 meters, and then 20 seconds and 3,600, because there's 60 seconds in one, then your answer is 10 meters per second. So now you have acceleration, 10 meters per second divided by 20 seconds, your answer is 0.5 meters per second squared. Now please, if you don't understand how I did that, then just let me know and we can work on it together. But you always want to get your answer in meters per second squared. So watch what these units are given to you in, and that's why I was telling you earlier, know how to convert a kilometer to a meter and an hour to a second, okay? So to convert seconds, there are 60 seconds in a minute, 60 minutes in an hour, so there's 3,600 seconds in 1 hour. And how do I know that? 60 times 60 is 3,600. And then that's how we get our answer. The next one is force. Now, force means it's a push, pull, or other action that changes the motion. So if it's trying to go and then you change the direction, it's equal to the mass of the object multiplied by the acceleration. The formula is F equals m times a. So I just did it ma, but here it is, force equals m times a. And m is mass, a is acceleration, and when you make this, or you complete one of these formulas, the answer is going to be in a Newton. So there's a Newton. And so here is a an example, you have a 55 kilogram mass accelerated at 14 meters per second squared. Okay, so there's the acceleration is based on velocity, and so you multiply 55 kilograms at 14 meters per second squared, and the answer is 770 newtons. So by doing that, that's how you would get that. Force is the mass of an object times acceleration. Okay? Then we have momentum. Momentum quantity is an object that is in motion, and the greater the velocity of the object, the more momentum it possesses. So it's represented by the letter P, so I have no idea why, but M was already taken. So P is momentum. This is mass times velocity. So if you were thinking about a problem, let's take that quarterback. It's by using this gentleman here who threw the football we saw earlier. If you have a 60 kilogram quarterback moving at 9 meters per second, so that's 60 kilograms times 9 meters per second, then the momentum is 540 kilograms dash meters per second. So it is the mass times velocity. Yeah, I hope you're not confused yet, because we have one more here. Well, we actually have a couple more. So now we have work. Work is a big W, and its measurement is in joules. Work is performed when a force is applied to an object and moving that object. It's an expression of the force applied to an object multiplied by the distance at where it went. So by doing that is two friends use a cumulative force of 1,080 newtons to push a car 218 meters. The work is the force times the distance, and you have 235,444 joules. That one's simple enough, right? Now let's take that and go to power. So when you're looking for power, notice P's already taken by momentum. Now we have watts, so it's a W. So power is work divided by time. So it's the rate of doing work, the amount of energy transferred, and the fundamental quantities of mass, length, and time are used to find power. Mass and length are derived from the use of work. So you already have to figure out what the work is, and then you're given the seconds. So right here, find the power of a man who pushes a box 8 meters with a force of 15 newtons in 6 seconds. So if you go back to this one and find out work, how many newtons by how many meters? So 15 newtons times 8 meters is 120 joules. Then to get power, it's 120 joules divided by 6 seconds. The answer is 20 watts. I know this sounds a little bit confusing, but now that you know how to do each one of these, there are some examples in your book, and you can go out somewhere else, or I can come up with some problems for you if you'd like. You'll just need to let me know, but I want you to work on how you figure out all of these different quantities, okay? Because it's very, very important. Now, once you have all of these derived quantities, I also want you to think about these concepts: inertia and energy. Inertia is the property of an object that resists change in motion. That means that the mass is a measure of the amount of inertia that a body possesses. It's solely based on mass, and all objects with mass have inertia. So whether it's a solid, a liquid, or a gas, it has inertia. Objects in motion have then momentum, and then momentum is the product of mass and velocity. So the inertia is not moving, but the ability to move. Then you have energy, which is the ability to do work. So if it's at rest, it resists change, but when it does change, it becomes energy. So this ability to work. And with the ability to do work for energy, we have two different states. We have stored state, which is potential, and then when it's expended, it's kinetic. So look at this. Here's a, we'll call this a wooden stake in the ground, and here's a big thing of weight. So it has a potential energy because it's just sitting there, and that would be inertia. It has that much energy available. You cut the rope and it falls, well then as it moves, it becomes energy expended, so that's kinetic. Along with energy, there's also different forms. Why is this important? Because a lot of these apply to radiology. Now, we have chemical, which means you put different components together and it creates a different matter. We have electrical, which can be from a battery or, which can then charge a light bulb, or it can be the switch, whatever. We have thermal, and then there's your thermal heating up your chemical energy, and then there's electromagnetic. So electromagnetic means that it's forces pulling against one another. So if you have chemical energy, then it's released from a chemical reaction. Why is that important in radiology? We used to have to process our films, and by doing that, you had chemical components of the solutions and the fixer, the developer, and all that good stuff. Great news, we no longer process films. It's no longer on our registry, but there are still some chemical reactions we may talk about with other things like our, here I'll throw it out there, photostimulable plates that you will actually work with. So know that chemical energy is possibly not as important as it used to be in radiology, but it's still something you need to know about. Then you have electrical energy, and then this is the flow of electricity. This is the electricity we usually think about, but you have to understand even a battery has electricity. It's just a different type of electricity. So when you have a plug, you stick it in the wall, then all of these things can happen. You can have heating and cooling with an oven or a refrigerator, an air conditioner. You can have light. You can have communication. Every one of you, I'm sure, has a computer. And don't you love this picture of this portable phone? I used to have one like that. I bet none of you do. Because now we have smartphones. But it still has to have some type of electricity to charge it so that it will actually work. And then here's some other components, a blender, a drill, and even a car. So if you have an electric car, send me a picture of it, because I'm seriously considering getting one the next time I need it. So why is this important? If we don't have electricity to actually make our unit work, we can't take an X-ray. So electrical energy is very important to radiology and imaging. And then there's thermal energy. Thermal is heat. That's the energy of motion at the atom or molecular level. You are making something happen at the molecular level, and it's measured by temperature. Now, if you think about thermal, let's look at this one first. We're heating a pot of boiling water. So this is a fire. Now, this is not the same kind of radiation that we get from an X-ray tube, but it's still radiation, and that radiation of heat is making this get hotter, and so this is the convection where it starts boiling, and then it conducts it into this handle. Why are our pots nowadays got rubber around this? Because if you didn't, you wouldn't be able to hold it. I still have a couple of older pots, and especially like my cast iron, that because the whole thing gets hot, I have to use pot holders. So, the conduction of thermal energy is very important. Now, this is an X-ray tube, and we'll get into that later, but this is the focusing cup, the filament, the high voltage circuit, the filament circuit, but none of that will produce an X-ray until we actually have energy that then makes these electrons boil and shoot out of the X-ray tube. That's why thermal energy is very important to us. Then there is electromagnetic energy. This is the most important type of energy for radiology because you need to know where we are, and if you've never heard of this before, the electromagnetic spectrum. This is something you will be asked to recite later. And where does X-ray fall on this electromagnetic spectrum? This is just one example. Your book has a few more, but this is the type of energy that we have in an X-ray photon. We will discuss this more in detail in Module 3, but just know for right now that where X-ray is very important. Electrons that move very fast are down here in gamma rays, and then as they slow down, they come all the way to radio. So X-ray is on the same spectrum as just listening to radio or microwaving our food, but these are not harmful because they have long wavelengths. We'll talk about those wavelengths later, okay? Now that we've talked about the fundamental quantities, the derived quantities, let's talk about radiation quantity measurements. These are the most important things that you need to know, but they won't make sense unless you know the basics ones. So here's one. This is what we call our British system. This is what you may hear your fellow techs talk about when you go to clinical. You'll hear me talk about it. You'll talk about this in lab, but you also need to know the SI units because you never know what may be used at the workplace. The Röntgen is the same as coulombs, radiation absorbed dose, or the rad, and then the radiation equivalent man, rem, curie. So here are their SI units. So let's just go straight into each one of these separately. What is the Röntgen? Guess what? It's named after the guy who discovered X-rays. But this is used to quantify radiation intensity. Remember this word, intensity. With that intensity, it's equal to the quantity that produces that many ion pairs in a cubic centimeter of air, and the SI unit is the coulomb per kilogram. So what it actually means, though, is that an ion pair is an electron that's removed from an atom, and then when the atom from which it came joins together, it creates an ion pair. With that, that is how much radiation you actually use. So the intensity of that is measured in a Röntgen. You may see the SI unit of coulomb per kilogram, but I can tell you in the real world, Röntgen is probably used more often. What I have not written here is that, remember back to this one, a Röntgen is just a big R, okay? So a big R for Röntgen. The next one that you need to know about is the rad. Rad stands for radiation absorbed dose. So a lot of people think, well, it's just radiation. No, the radiation intensity is your Röntgen. This particular unit is used to describe the biologic effects of radiation on humans and animals. And so that means it's absorbed. When we take an X-ray, and we'll learn all this later, but that X-ray leaves the tube, goes through the patient, and then only a part of that radiation comes out the other side to make your image. What is left in your patient is the rad. That's how much they absorbed. And it's the amount of energy deposited. And the SI equivalent is the gray. There's you another symbol right here. 1 rad is 10 to the negative 2 gray, or 0.01. So we went 2 places. So here was a 10. You go 1, 2. And then to convert rads to gray, multiply the rad value by 0.01. 1 rad equals 100 grays. Now, 100 gray, 0.01. There's tenths, there's a hundredths. This is very important because every bit of matter, here's our ionizing radiation, and it may not be as easy to see on this example, but we'll see it again later. This amount is bigger than what comes out the exit, and what stays behind is the absorbed energy. So rad is what we do to our patients, okay? Then we have REM. Radiation equivalent man. That's what REM stands for. It is what quantifies the occupational exposure, or the dose equivalent. So even us as a student, and then when you become a radiologic technologist, we are always susceptible to radiation that leaves the patient. So that occupational exposure is what happens to the exiting radiation that may possibly be in the room that then hits you. Now, number one, if we're not out there, then we're not going to get it, but it could happen anyway. The SI equivalent is the sievert, which is SV. 1 rem, 10 to the negative 2, 0.01, or 100. So it's very similar to the rad. Just know that the difference between these two is patient absorbed, technologist exposed. Okay, we should not be exposed, but sometimes it happens. And then we have the Curie. The Curie is used to quantify radioactivity. Now, this is not how much radiation is emitted, but how much something is radioactive. Now, this means 1 Curie is where 3.7 times 10 to the 10 atoms disintegrate every second, and that's how it's decaying. Disintegration or decay is the process where that radioactive atom gives off particles and efforts. Now, will we be working with anything that's actually radioactive? No, you should not be. But the reason this is an important term is because in a department, they may have nuclear medicine, and nuclear medicine encompasses the radioactive material that we actually inject into a patient. And then that radioactive material is processed in the body and then eliminated through waste, and then we take photographs, just plain old photographs of where that radiation was. So there's our Curie. It's equal to the SI becquerel, and there's some numbers for you. Is that as important in what we do every day as a radiographer? No. We use these units of measure and you need to know them, but understand, just recognize that this is quantifying radioactivity, not something in your typical X-ray machine. Okay, now let's look at some equipment. Now that we know what we're using and how we obtained it, let's look at your typical radiographic equipment that you will work with. Now, all of you have already been in the lab at your respective campuses when you were working in patient care, so you already know what you have in your facility, but these are just some examples of what you may see once you get to go to clinical. And passing this particular course helps get you there, okay? So this is important to know. This is a tabletop that does nothing but X-ray because it's just a table and a tube. This is a console that goes with this one, and this table, the reason this is out here is because the tube is underneath. This is a fluoroscopy table. You shouldn't have one of these in your lab on your campus, so this may be the first time you've actually seen this. Now, there are two different types of radiographic equipment. One's mobile. That means it's mobile. It moves. This is a portable unit, and it's on wheels. And anytime you use it, though, you need to also take your shielding with you. Permanent equipment means it's in a room, it stays there, you don't tote it around, and then the shielding is in place. Today, this week, we're only going to talk about permanent equipment. We'll talk about the mobile later on, and by doing that, then we'll start talking about the applications of it. So for right now, we're going to basically go with just permanent. Here is the main part of equipment. Now, you have the operating system, which is this stuff right here, and then you have a high voltage generator, which is these two components, and then you have the tube itself. So the operating system includes the tube, the stand that the tube is on, the table, and then the upright bucky, and the console is where you actually input the techniques that you use to take an X-ray. We will also talk about that much later in the course. And in fact, Chapter 5 is going to get into the tube itself and what KVP and mass are. So, when you look at the tube head assembly, it's important to know that this entire tube is part of your permanent equipment. Now, there is also this little box right here, which is your collimator box, and if you haven't already, you will at some point this week go and work with the equipment in your lab, you're not going to take an X-ray exposure, but you'll play with the collimator and know what you're doing. You'll see a light coming out right here, and where you open and close these collimators is how much radiation that you're actually letting come through there. Then there's the tube stand, and the stand, here I'll go back one real quick, is this right here. So all of this apparatus is the tube. Here's the collimator, and then it's standing on that stand. So here's the tube stand or mount. So permanently installed equipment has the tube right there, the collimator right here, the table, the control units, which are not in this picture. Well, I mean, this is the collimator control, and then these are the things that you can use to move the tube around. And then we're going to talk about those later. And then you have the different variations. This is a floor to ceiling right here, so it goes all the way to the top. But this tube can move up and down on this. This also probably goes to the end of down here, and then you flip the tube so that you can take a chest x-ray. Then there is a ceiling mount. So notice this just has, there's no stand, so you've just got this tube coming out of the wall. You will probably see this type of equipment in an emergency room department, and I've even worked at facilities where they had one of these, and then they had the curtains between 2 or 3 different exam rooms, and that X-ray tube can be taken to all 3 of them if you wanted to, so that they don't have to put equipment in every single room. But no matter what, you're going to see a tube, we're going to see a table, and then you're going to see this generator. That generator has to be somewhere. So the tube stand or the tube mount is the portion that gives mobility to it, and this lets the radiographer the flexibility to image from a variety of angles. Again, you will practice that in lab, playing with it, moving it, shooting back and forth, not really taking an x-ray, but at least working. And then the floor mount has a horizontal track, and then you have the overhead tube, you know. So here's a couple of different variations. And then the table. Most of the tables you will work with, and I don't know if this is what you have in your lab, but hopefully you do, this goes up and down. Now, back in the old days, we had tables that did not go up and down, so you had to use a little step stool. And if your patient couldn't get up on the step stool to get on the table, then we had to pick them up. But not only with this does it go up and down, you can click a pedal and then it has a floating top. So hopefully you'll get to work with that in your lab also. And the reason that this has just all changed so much is because we've come out with better equipment and material. So it used to be real heavy metal. Now we're using some polycarbon something that makes it lighter and makes those things easy to go up and down. You will also find out that every table has a weight limit. Now, if your weight limit is 400 pounds, but you have a 450-pound patient, you could probably still put the patient on the table, but you cannot use the mobility functions, meaning you cannot make the tabletop float and you cannot make it go up and down. So the weight limits are put on the hydraulics of the system, and that's something that's very important to know too. With the fluoroscopy table, and I showed you one at the beginning, those tables will stand up so that the patient can stand up, or they can lay down. This type does not. It stays flat always. And then you have the wall unit. So this is usually used for chest x-rays, but it could also be used for C-spines and some other things. I've even, if I have a patient who just cannot lay down because they're in so much pain, I've done arms and legs, whatever needs to be done. But you always want to use this for your chest x-rays and possibly an erect abdomen, just so that you can get that. But here's that, the way that this is made, and that thing flips around so you can get the x-ray that you need. Here's your control panel, and right here is how you select your KVP, which stands for kilovoltage peak. I said kilo, it's kilo. And then here's MA, which is milliamperage, and then your time, which is in seconds. Those two things together give you mass, which is milliamperage per second, and then you can fine-tune or modify your exposure parameters. All of these features are different depending on the control panel that you have, but from a physics standpoint, know that these control the electricity that's applied to the tube to produce X-rays. So when we're talking about the electrical energy, you are setting your controls even if you use an automatic exposure control, because you're saying this is how much I will need for this particular exam. Here's another concept that you need to know about. Even though we're just starting off in physics, you need to know that every time you take an image, which will not be for a little while, and that means that it should be as low as reasonably achievable. Any exposure that you should make the least amount of exposure so your patient's not getting radiated, and that you are not getting any extra dose that you don't need. It is our responsibility to minimize radiation to your patient, to yourself, and to others. Which sounds silly, but if you're in a room, keep the door closed, because if that X-ray, it doesn't stay contained, it can pass through materials, and if it's an open door, that could be a problem. So you'll hear this concept a lot more as we go on around by the end of this, and then you have another whole course on radiation protection where you'll hear ALARA a lot, okay? Now, you've probably already touched on these organizations in your Intro to Patient Care. These are extremely important to us as students as well as radiologic technologists. But the American Registry of Radiologic Technologists, or www.aort.org, if you've not already been there, you need to know that they actually have a code of ethics, and that code of ethics states that you are required to always use the concept of ALARA. Now, this is the certification area. They are the ones that give the test to qualified students who have completed the correct and appropriate educational course along with clinical, which is another plug. I want you to go out there and look at the content specifications that I've put out there for you. And then you have the ASRT, which is the American Society of Radiologic Technologists. They have professional resources. Here's their website if you have not already been there. The ASRT also provides the practice standards. And with the practice standards, that means what you can and cannot do as a radiologic technologist. And this association is who the public will refer to when they talk or they have a question about what a radiologic technologist can do. So can someone actually use a fluoro table, or does it have to be the radiologist? So know the difference between these two and why it's important to the concept of ALARA. Here's another fundamental of radiation protection that you need to know about, and it's called time-distance shielding. I'll make it as short and simple. The less time spent near the source is the less radiation. So the time also has to do with your patient. You make the shortest exposure you can with the best exposure factors, but you also don't stand out in a room when someone has an X-ray. Distance, the greater the distance, the less radiation. This has to do with you and your patient. You need to be as far away from the X-ray source as possible. You'll see that your X-ray machines have exposure buttons on a cord that can only go so far. And when you take an X-ray of a patient, you want the tube to be away from it. The closer the tube is to the patient, the more intense that radiation is. We'll talk about all that later too. And then shielding. If you are standing behind the shielding, then you will get less radiation. If the patient is getting a chest X-ray, then you can shield the lower half of their body and they're getting less radiation. These are very, very important things that we will continue to cover as time goes on. Another tool for radiation protection is the field of X-ray exposure, limiting it. So if that's the collimator, you'll do that in your lab, you'll talk about it, you'll actually work with those controls, see what it means. You'll also work with the KVP and mass, and you'll understand by the end of this quarter exactly how to use the appropriate KVP and mass. You always need to avoid unnecessary duplicate exams. You need to screen for pregnancy because we will learn why it's much more harmful to a growing baby. And the bottom line is this: do it right the first time. So if you do it right the first time, you have minimized exposure to your patient, exposure to yourself, and exposure to the public. And we'll talk about how the greater volume of tissue we expose. Chapter 7 has a discussion of interactions with matter. All of these things are going to be very important for us. And then there's a number of daily workflow tasks that we'll talk about that address radiation protection. And it's just a whole bunch of things, and we're just started on it. I know y'all are, if you actually listen to this whole thing, I really want to applaud you. I hope I didn't bore you to death. But what did we talk about? Who discovered X-rays? Make sure you know that. Who and when. So when were they discovered? What were the first radiographs taken? Know that it was of his wife was the first one, and then of his associate was the second, and then all of the people that over the years have lost body parts and their lives being their first pioneers of radiography. Then what are the different types of energy? What are the fundamental quantities of physics? Why they are important? To find the derived quantities and what they are, and then how those are used for the radiologic quantities, because that's what we do here. And then what are the fundamentals of radiation protection? It seems like a lot in this chapter. It is a lot, but a lot of it is more information to get us started. And you've got some assignments, and I can't wait to see them coming in. And not only that, you're going to have fun in lab, okay? So here's just an example. These are actual X-ray images of some butterflies. And so it's not just patients that we X-ray sometimes. It's just really cool to look at other objects too. So thank you for your attention. I hope we have a lot more fun in the future. Bye.